How are you all doing today?
Pretty all right. How about you?
Doing good. I apologize. I thought I had muted myself when I was goofing off on my guitar, so I'm sorry that you had to hear me butcher some Van Halen. Um,
It was nice background music or elevator music. That's what they call it.
well, thank you, but you're live. All right, so I'd like to talk about the mini labs real quick before we jump into today's lecture topic. So I have created a tab on the side of our Moodle page. It's at the very bottom and it says mini labs. So if we click on that, there are 2 assignment sheets and then 2 submission portals. By the end of the quarter, there will be 8 of them up. They are all due on August 13th, which is the last day of the quarter at 5 p.m. These are individual assignments. And so I'm going to take a look at this first one here. So what I've done is effectively done the lab for you and collected all of the data. So all of this stuff that has anything to do with using the Explorer board and its subsequent software package is entirely unnecessary for you all. So this first experiment involved applying a specific voltage drop over a resistor and then measuring the current flowing through it. And so that is exactly what I did. The voltages written in blue in parentheses are the actual voltages I measured with a multimeter because it's hard to get fine detail on the voltage source that I was using. And then I measured the current in milliamps to go with each of those applied voltages. So what I would like you all to do, and it's detailed here in the sheet, is plot the data in Excel. You can either use my exact voltages or you can just use the approximate voltages. It really shouldn't matter in the grand scheme of things. And plot it in a graph with current versus voltage and then create a trend line. So where there are blanks left over, like for where it says equation and r squared, etc., that's the part that I want you guys to fill in. You don't have to actually give me or send me your plot or anything. You just need to tell me what your trend line is, tell me what the r squared value of the trend line is, and then figure out what units the slope should have. So all that depends on whether you plot current on the y-axis or current on the x-axis. If you plot current on the y-axis and voltage on the x-axis, your units would be in Siemens. And so this second question here, how does the slope relate to the resistance value? The slope of the line would be the inverse of the resistance value, so you would get the conductance from your trend line. And if you plotted it with voltage on the y-axis and current on the x-axis, obviously then the units would be ohms and the slope is the resistance value. So whichever one floats your boat doesn't bother me. Then I repeated the experiment with a different resistor, and you'll do effectively the exact same thing. This last question of why does the 10 ohm resistor get warmer at 2 volts than the 510 ohm resistor at 9 volts? You can completely ignore that question, but I can tell you what the answer is. The 10 ohm resistor is absorbing more power at 2 volts than the 510 is at 9 volts. So any questions on mini lab assignment number 1? It's really just taking the data that I collected and then doing a little bit of analysis, and then you're good to go.
Cool beans.
All right, so let's look at mini lab number 2 real quick. So this guy goes directly in line with what we covered in class on Thursday. There are 4 resistors. I collected their actual resistance value, and then I created the circuit shown below on a breadboard, and then measured the various combinations of resistances. So what I am asking you to do in this particular problem or assignment is to use these measured resistance values up here and to calculate the equivalent resistance seen between those terminals. So for example, if we were looking at the resistance seen between terminals A and B, that would look like the resistance of the 20 kilo ohm resistor in parallel with the series combination of the 1 kilo ohm resistor, 2 kilo ohm resistor, and 5 kilo ohm resistor, right? because we have two different paths to go from node A to node B. We can go straight down through the 20K, or we can go around the outside loop through those three resistors in series. Similarly, the resistance between terminals A and D would be 20 in series with 5, in parallel with 1 in series with 2, et cetera, et cetera. So you just use the measured resistance values and then use that to determine the resistance between the different, the different terminals. There are a second and third part where in the second part, you're asked to connect a wire between points A and D. So for you guys, that means you're connecting a short circuit. So there's just going to be a 0 ohm resistor effectively connecting points A and D, and then you'll do your calculations again. And for the third part of the mini lab experiment, you place the short circuit between B and C, and then again, calculate the resistance between those 5 terminal pairs. Any questions regarding mini lab number 2? All right, so the next mini lab assignment has to do with voltage division, which is what we're going to talk about today. So I'm going to try to do that experiment probably after tomorrow's class meeting, and then get that mini lab assignment sheet uploaded tomorrow afternoon, so that you guys, again, have the rest of the quarter to work on it. So with that out of the way, let's get to today's lecture. It's really 2 topics that we're going to talk about today. Can everybody see my engineering paper screen?
Yes, sir.
So today, our first topic is going to be that of, let me use not orange. Our first topic will be source combination. And our first source that we're going to be looking at specifically is voltage sources in series. So let's say that I have the following circuit, where I have some voltage V1 in series with some resistor R1. Let's do a voltage V2 that's also in series. And then finally, some voltage V3 in series as well. I'm going to label my resistor voltage drop as VR1, positive polarity on the left, negative polarity on the right, because I'm assuming our current I is leaving the positive polarity terminal of voltage source V1 and flowing clockwise around our loop. So if I were to write a Kirchhoff's voltage law expression, what I would have is negative V1 plus VR1 plus V2 minus V3 is equal to 0. So before we move on here, does everybody agree with the signs on the 4 different components of this equation? Yeah, so what I did is I started at this bottom left-hand corner, and whenever I see the negative polarity terminal first, it gets a negative sign. If I see the positive polarity terminal first, as I follow the current around this loop, I use the positive sign. So that's why everything has the sign it has. What I'm going to do now is I'm going to move everything, like all of the voltage source voltages to one side of the equation and the resistor voltage to the other side. So that would look like VR1 is equal to V1 plus V2, I'm sorry, V1 minus V2 plus V3. From the perspective of the resistor, then, we can see that it sees an equivalent voltage, VEQ, is equal to V1 minus V2 plus V3. Where our directions for adding together our voltage sources are simply those that have the same polarity. So the current enters the negative terminal first, get added together, and from that we subtract the voltage where the current enters the positive polarity first. So this might seem weird and abstract, but we actually do this all the time. In fact, you guys have done it before. If you recall, in Engineering 120, you were asked to build a power supply or a power pack for your robot kit, right? So it was a black box. There was a red wire coming off of it and a black wire coming off of it. And then you put in your batteries, which I'm going to poorly draw some batteries here. Looks like I might run out of room. Yeah, so this particular battery pack is only going to have 5 batteries because I ran out of room. That's okay. So these guys were actually wired up internally like so. So this was actually 5 1.5 volts, or in you guys' case, 6 1.5 volt batteries in series. And overall, it created a 9 volt source, which was used to power your robot. Okay, so anytime you've put 2 batteries together in a remote control, you have done voltage combination. And this is the reason specifically why, if you put one of the batteries in backwards, your remote control or whatever doesn't work, right? If you have 2 1.5 volt batteries and you put them in this configuration, so positive polarity, negative polarity, and then negative polarity, positive polarity, like so, into your remote control, it doesn't work because it sees a potential of effectively 0 volts. But if you were to put it in this way with them correctly, it sees a potential of 3 volts and starts to work. So does anybody have any questions about adding voltage sources together in series? I tend to not spend a whole heck of a lot of time on this because you guys have fundamentally been doing this for any time you've had an electronic device.
I think we're good.
All right, so now let's talk about voltage sources in parallel. And this one is a particularly odd discussion, okay? Or it can be a little odd. So let's say that I have the following circuit where I have some voltage source V1 connected in parallel with some resistor R connected in parallel with another voltage source V2. If V1 and V2 are identical, everything is okay. If V1 does not equal to V2, everything is broken. Let me explain what I mean by that. Let's say that I'm trying to find the voltage source, or excuse me, the voltage drop over this battery. Well, I'm going to call it VR, okay? If V1 is 5 volts and V2 is 4 volts, what does Kirchhoff's voltage law tell me the voltage drop over my battery is? So if I go around this left-hand loop, KVL tells me that the voltage is 5 volts. And if I go around this right-hand loop, KVL tells me that the voltage is 4 volts, but it cannot be both 5 volts and 4 volts simultaneously. So here is the problem with combining voltage sources in parallel. If we have two equal voltage sources in parallel, we can treat it like it was one voltage source. If we have two unequal voltage sources in parallel, we cannot analyze the circuit because circuit analysis techniques break down. Now, in practice, like we could physically go set up a circuit that works just like this. And what we would see when we short out these two unequal voltage sources between each other is that the wire that's used to short them out is going to get really, really hot. So that is the reason why you were told in your engineering 120 class to always take the batteries out before you soldered on the barrel jack to connect those wires. Because effectively what you had is if those wires touched each other inside your bag or whatever, you had 6 volts in parallel with 0 volts, and that causes a large amount of current, literally all the current that those batteries can supply, to pass through that wire that's shorting it out, trying to bring it up to a potential of 6 volts, causing everything to melt. So you can literally start fires by shorting out a battery. So one thing that you may be asking yourself is, well, if applying voltage sources in parallel can potentially be bad, why would we ever do it? And in practice, it's done a whole heck of a lot. So I'm going to draw what is probably going to be a terrible picture here. This box is supposed to represent a solar panel. And it has a voltage rating of, let's say, 12 volts and a power rating of, let's say, 48 watts. If I connect another solar panel, which is just a voltage source, it has a voltage of 12 volts, and it has a power rating of 60 watts. Well, if I tie these guys together, the voltage drop across my terminals is still going to be 12 volts, but I can now supply a total power of 108 watts. So we connect solar cells and stuff like that in parallel in order to effectively get more current out of the system or increase the power production efficiency of the system. So it's probably more likely, instead of just seeing two solar panels connected together, we might see a system that's more like this. So if this is a 12 volt, 48 watt one, this is another 12 volt, 48 watt, 12 volt, 48 watt, 12 volt, 48 watt. If we wire up a system like this, we can actually output 24 volts at a total power of 196 watts, which means, so if we look at just this solar panel in the top left, if it's rated for 48 watts and 12 volts, what is the maximum amount of current that can safely be supplied by that particular solar panel?
Could you repeat the question?
If the solar panel is rated for 48 watts and provides a voltage of 12 volts, what is the maximum amount of current that can be safely provided by the solar panel? Four amps, absolutely right. So this guy is providing 4 amps. So we might have a current up here of 4 amps. All of these would be rated to supply at most 4 amps. Well, we have 4 amps in series with 4 amps, which just looks like 4 amps. But then we have another 4 amps in parallel and another 4 amps in parallel. And as we'll see in just a moment, when we add current sources in parallel, the currents add together. So by putting these voltage sources in parallel, we are increasing their current carrying capabilities of the system. My job outside of being a professor at Louisiana Tech is I work for a company called Sabre Industries out of Bossier City, Louisiana, and I work on designing battery energy storage systems. In our battery energy storage systems, we have literally hundreds of cells tied together in series to create a 1500 volt battery. And then we usually have anywhere between 20 and 60 of those battery banks tied together in parallel to output as much as 4,000 amps of current on purpose. And those large battery energy storage units are used to power parts of the San Diego Zoo and stuff like that. And they're used as a supplement to the grid to lower, effectively to provide power when buying energy from the utility is expensive. So in practice, combining voltage sources in both series and parallel is done a whole heck of a lot, especially in alternative energy applications. All right, the next thing that I want to talk about is current sources in parallel. So let's say that I have the following circuit where I have some current I1 in parallel with some resistor R in parallel with some current I2 in parallel with some current I3. I'm going to define my resistor current to be IR, direction down, like so. And if I apply Kirchhoff's current law to my top node where currents leaving are positive, I get negative I1 plus IR minus I2 plus I3 is equal to 0. And I'm going to do something similar to what I did when we had voltage sources in series. I'm going to move the current flowing through the resistor to one side of the equal sign and have all of the current source currents on the other side. And that would give me IR is equal to I1 plus I2 minus I3. And so from the perspective of the resistor, it sees a total current of IEQ is equal to I1 plus I2 minus I3. And so the convention here is that current sources that are in parallel, when they have the same direction, they add together, and when they have opposite directions, they tend to cancel each other out. So if I had a system like so, where I had a 3 amp source up, a 2 amp source down, and some resistor here, the resistor would see a total of 1 amp of current flowing through it. But if I had 3 amps up and 2 amps up, those resistor would see a total current of 5 amps flowing through it. So that's how we combine current sources in parallel. Current sources in series are another odd duck, like voltage sources in parallel. So if we have current source I1 in series with some resistance R, in series with some current source I2, like so, if I1 is exactly equal to I2, everything is okay. But if I1 does not equal I2, everything is broken. So for instance, let's say that I1 is 1 amp and I2 is 2 amps. As we follow our current around the loop, we can see that 1 amp of current enters our resistor R, but 2 amps of current leaves, which means our resistor R somehow destroyed 1 amp of current. Well, destroying 1 amp of current means that it has destroyed 1 coulomb of charge in exactly 1 second. So this situation violates the law of conservation of charge, because charge can't be created or destroyed either. It can just be transferred around. There isn't a real practical application of adding current sources in series, and it's because of the way current sources are actually implemented in real life. It's a transistor-based circuit. So our closest thing, closest practical application of combining current sources in series would actually be this solar panel example I've already worked, where since this top left solar panel has a rating of 4 amps, so let's say this guy down here was rated for 60 watts. That would mean that it could actually carry a current safely of 5 amps, but it won't, because it's limited by the smallest current in the system, right? So if everything, if the lowest amount of current that can be passed in this branch is 4 amps, then only 4 amps is going to wind up flowing through it. So even with this change, the output power of the system would still be exactly the same. All right, so our next topic, and it's 2 topics really, is current. Oh, actually, let's work an example problem. My computer will. So let's say that we have the following circuit. This is a 12 milliamp source. We connect it to a dependent voltage source, excuse me, dependent current source, whose value is 0.03 VY. That is in parallel with a 10 kilo ohm resistor, whose voltage drop is Vx. And this is in turn in parallel with a current source having 3.5 milliamps direction down. There's a second portion of the circuit over here on the right where we have.
Professor, is that 101 ohms or 100 or 10 ohms for the VX?
10 kilo ohms. Let me write that.
Okay, sorry, I was like, what?
Nope, no problem. 10 kilo ohms. All right, thank you. Let's say that we have a 1 kilo ohm resistor here. A -2 milliamp source like so. And this is our voltage drop, Vy. And our ultimate goal in this problem is to solve for what Vx is equal to. All right, so any thoughts on how we might approach this problem? Anybody throw anything at the wall and let's see if it sticks. All right, nobody's. I'm sorry.
Well, we gotta figure out where everything's going, so there's one thing we have to do.
All right, so let's see. So I'm going to do something here. I'm going to say, I'm going to call the current that's flowing down through this 10 kilo ohm resistor as Ix. All right? Because I know that my voltage drop over that 10 kilo ohm resistor is going to be that current Ix multiplied by 10 kilo ohms. Are we in agreement there?
Yes.
All right. So what I can do to start things off here is I can observe that there are 3 current sources in parallel. One of them happens to be a voltage controlled current source, but it's still a current source. So I can actually combine them together. And so what I mean by that is I could say that Ix is going to be 12 milliamps plus 0.03 Vy minus 3.5 milliamps, right? So the current sources with their directions up added together, and the current source having a direction down is subtracted. I could simplify this. 12 minus 3.5 is going to be 8.5 milliamps plus 0.03 VY. Does anybody have any problem with that? And I could get this exact same result just by applying Kirchhoff's current law at this top node. But the whole point of being able to combine current sources together is to really kind of skip that step.
You left out your 0.5 for the 8 milliamp.
Oh, thank you.
Yeah.
8.5 milliamps. Okay, thank you. So now that we know, or we have a better understanding of what IX is and how to solve for it, we need to figure out how to determine VY. Any thoughts?
You apply KVL.
Yes and no. And so the reason why I'm saying yes and no is that if we applied KVL around that right-hand portion of the circuit, we would have negative VY plus VY is equal to 0, which doesn't tell us anything because that's just 0 is equal to 0. So if we start here, we see the negative polarity terminal of VY as the voltage drop over the 1 kilo ohm resistor. And then when we come down the other way, we see the positive polarity terminal of VY. And so we just get effectively 0 is equal to 0. Instead, let's apply Ohm's law, right? Because we know that there is a fixed current flowing through that resistor. So I'm saying that VY is equal to my 1 kilo ohm resistor multiplied by the current that's flowing into the positive polarity terminal, which is positive 2 milliamps or negative 2 milliamps. So chat says negative. Unfortunately, that is incorrect. So let me explain what I mean by that. I'm going to erase this VY right here. I'm going to move it over, right? So does it break anything for me to write VY like that? Attach it with that 1 kilo ohm resistor on the left and attach it with that negative 2 milliamp source on the right. So this probably tells you a little bit better why KVL isn't really doing much for us. But we can also see that as this current flows around, it's flowing into the positive polarity terminal first. So because it's flowing into the positive polarity, oh wait, actually, sorry, Mr. Gray, I think it was. Yeah, you are correct that there should be a negative sign there. I'm confused myself with my own question. So negative 2 milliamps is flowing into the positive polarity terminal, giving us a voltage VY is equal to negative 2 volts. If we substitute this in, we get 8 IX, running out of room here. IX is equal to 8.5 milliamps plus 0.03 times negative 2 volts. So what are the implied units on this 0.03? Anybody remember that from our first lecture? amps per volt. That is correct. So if we multiply 0.03 amps per volt times negative 2 volts, that is effectively negative 0.06 amps or 60 milliamps. So IX is going to be 8.5 milliamps minus 60 milliamps, which gives us negative 51.5 milliamps. Finally, we could say that Vx is simply Ix times 10 kiloohms. Can't write kiloohms to save my life today. So negative 51.5 milliamps times 10 kiloohms. So 51.5 is going to be negative 515, or 51.5 times 10, the negative sign, and then a milliamp and a kiloohm together gives me a volt. So the correct answer is negative 515 volts. I like to ask questions like this, but there's a part of it that some students may find a little bit confusing. So I'd like to talk about it real quick. Okay. And the issue that some students may have is what's going on with this chunk of wire right here, which is effectively connecting the right-hand side of the circuit to the left-hand side, and why it doesn't particularly do anything. So an argument I get a lot in class when I teach this in person is that since that piece of wire is there, some of that 2 milliamps of current should branch off and potentially flow to the left into the left-hand portion of the circuit. And similarly, some portion of the circuit, overall current flowing on the left-hand side might branch off and flow to the right, interfering with that small loop. If we apply Kirchhoff's current law, we can see that there is negative 2 milliamps of current flowing out to the right. And similarly, there is negative 2 milliamps of current flowing down. So if we apply KCL at this node, we find that these two currents exactly cancel each other out, which means no current can flow to the left or the right through that section of wire. All that wire is doing is, or what I'm trying to show with it, is that the right-hand side of the circuit is coupled to the left-hand side, meaning we should treat it as one circuit. So, all right, any questions on this example problem?
No, sir.
All righty. So now let's get to voltage division first. And you guys may have talked about this a little bit in your Engineering 120 series. So let's say that I have a resistive network. Some resistor R1 in series with some resistance R2 in series with some resistance R sub n, like so. And let's also say that there is some known voltage drop across this series combination of resistors. So I'm intentionally not drawing a source here because we don't have to have a voltage source present to be able to apply voltage division at all. We just need to know what the voltage is. Since all of these resistors are in series, they will all carry the same current, and I'm going to call it I naught. All right. So I could say that V naught is equal to I naught times R1. Actually, let me go back one quick step here to make this a little bit more clear. I'm going to call I naught this guy right here. Let's call this voltage VR1, this voltage VR2, and this voltage VRN. So I could say that V naught is equal to VR1 plus VR2 plus VRN from Kirchhoff's voltage law. I can express all of my resistor voltages in terms of that current. So that would be I naught times R1 plus I naught times R2 plus I naught times Rn. And finally, I could group like terms together and say that this is simply I naught times R1 plus R2 plus all the way out to R sub n, right? Up to this point, this is exactly identical to what we did to combine resistors in series. But let's take a quick aside here. Let's express I naught in terms of those resistor values. So I naught is V naught divided by R1 plus R2 plus Rn, like so. Well, the voltage drop over resistor R1 has to be R1 times I naught, which would be V naught times R1 divided by R1 plus R2 plus R sub n. Similarly, the voltage drop over resistor R2 would have to be R2 times I naught, which would just be V naught times R2 divided by R1 plus R2 plus all the way out to Rn. So these equations that I've developed here, and I could develop more for other resistors, but it's really pointless because they all follow the same form, let me know what the voltage drop over any resistor in a series of resistances is without ever actually bothering to calculate the current. Now, for the simple circuits that we've been dealing with, this isn't really going to be a whole heck of a lot of a time saver, but we will get to a point where applying the principle of voltage division will really simplify analysis of some ugly looking circuits, okay? So our general rule here is that the voltage drop over the kth resistor in series is simply the voltage drop across all of our resistors in series multiplied by the kth resistance divided by the sum from I is equal to 1 to n of all of our resistors in series, or put in a slightly less terrifying way, V naught multiplied by the resistor we want, which I'm calling RK, divided by the equivalent resistance of all the resistors seen by that voltage V naught. So let's say that I have the following circuit. And I want to find out what that voltage V2 is. Applying voltage division, I can say that V2 is just 5 volts multiplied by 2 ohms divided by 3 ohms plus 2 ohms is equal to 2 volts. No current had to be solved for at all. Now you may say, well, this is quick and arbitrary and easy. We could have just solved for the current and then figured it out from there very, very simply. So let me make things slightly more complicated. Let's say that I have 10 volts, an 8 ohm resistor here, 4 ohm resistor here, and a 10 ohm resistor here. And I want to know this voltage V4. I can still apply voltage division even though all of the voltages aren't connected in series as follows, okay? So V4, which is really the voltage drop over the 4 ohm resistor and 10 ohm resistor in parallel, is going to be 10 volts, my known voltage drop, multiplied by 4 ohms in parallel with 10 ohms over 8 ohms, which is in series with that parallel combination of 4 in parallel with 10. Give me just a moment. I'll throw this in my calculator and we'll see what it is. (50/19) or 2.632 amperes. Sorry, that's not wrong. Or excuse me, that's not correct. 2.632 volts. So we solved that guy without ever finding the current flowing through the 4 ohm resistor, where finding the current that's actually flowing through that 4 ohm resistor that we have shown here would actually be probably one of the hardest questions I could ask you to do right now. One thing that I do want to point out is that the polarity of the voltages that we find absolutely matter. And so what I mean by that is that if I have this circuit, I put the positive polarity on the bottom, V14 in this case is going to be, if we apply voltage division, we're going to have V8 or 8 volts. Then we're going to have 14 ohms over 24 ohms in total. But we're also going to have to apply a negative sign. And the reason why we have to apply the negative sign is because the polarity of the voltage that we are trying to find is not what we would expect for voltage division. So let me go up here real quick to show you what I mean. When I assigned all of these voltages, I had effectively positive polarity of the resistor voltage connected to the positive polarity of the known voltage. But in this case, the negative polarity of the resistor voltage is connected to the positive polarity of the known voltage. And so that's where that negative sign has to come from. And if I do the math here, I have 8 times 14 over 24. Negative 4.6 volts repeating. So we are going to use voltage division a whole heck of a lot in this class. So we're going to get lots and lots of practice with it. So I'm going to move on to current division, and then we're going to work a problem that incorporates both current and voltage division, and then we'll wrap up for the day. All right, so in current division, let's say again that we have a resistor network, but now all of our resistors, R1, R2, etc., are connected in parallel. And let's say that we have some known current, I naught, that's flowing into this parallel combination of resistors. Again, it's not particularly important that we know that we have a current source explicitly there. We just know how much current is flowing in. I'm going to define this current as IR1, this current as IR2, this current direction down as IRN. Well, if I apply Kirchhoff's current law, I can see that I naught is equal to IR1 plus IR2 plus IRN. Since all of these elements are in parallel, they share a common voltage. I'm going to call V naught, like so, where the current is flowing into the individual resistor currents are flowing into the positive polarity terminal of voltages. And so what that is going to give me is I naught is equal to V naught over R1 plus V naught over R2 plus V naught over R3. And I can combine all of those terms together, and it'll look something like this. I naught is equal to V naught multiplied by 1 over R1 plus 1 over R2 plus 1 over R3. Sorry, that shouldn't be R3, that should be Rn. My apologies. And I can now define V naught, the common voltage, in terms of just my known current and my resistor values, right? So V naught is going to be I naught divided by 1 over R1 plus 1 over R2 plus 1 over Rn. Now, I'm going to do something here, which is really just an aside, but it's going to help us really figure out what this guy is doing here. So if I have I naught times 1 over 1 over R1 plus 1 over R2 plus 1 over Rn. What does this term on the right really represent? REQ. Exactly right. Specifically, the equivalent resistance of N resistors connected in parallel. So I'm going to call this guy REQ comma P for the where the comma P is because it's in parallel. All right, so using Ohm's law, I can say that IR1 is equal to V naught divided by R1, which is I naught divided by R1 divided by 1 over R1 plus 1 over R2 plus 1 over Rn, or expressed in a slightly different form, I naught is REQ divided by R1. Similarly, I could say that IR2 is V naught divided by R2, which is I naught over R2 divided by 1 over R1 plus 1 over R2 plus 1 over Rn, which is the same as I naught times REQ. Doesn't look like a Q at all. REQ comma P divided by R2. And I could keep going for all of the individual currents. So I can see that in general for current division, the current flowing through the kth resistor, IRK, is I naught times 1 over R sub K, the resistor I'm interested in finding the current through, divided by the sum of the inverse of all of the resistances in parallel. So 1 over R1 plus 1 over R2 plus 1 over Rn, which is the exact same thing as I naught times REQ comma P divided by R sub K. So to give you guys some help about how this is used, let's say that I have the following circuit. Sorry, 2 ohms. One ohm. And I want to know the current flowing through that 2 ohm resistor. Okay. Now, this network is not a bunch of resistors in parallel connected to a current source. But this is still the perfect time to apply current division. And the reason I say that is because we know how much current is flowing through the 4 ohm resistor. So we know for a fact that 3 amps of current is flowing into this network containing the 2 ohm resistor in parallel with the 1 ohm resistor. So using current division, we can say that I2 is 3 amps, the known current flowing into the resistor network, multiplied by 1 over 2 ohms. So that's 1 over the resistor we want the current flowing through, divided by 1 over 2 ohms plus 1 over 1 ohms. So we add together the reciprocal of the resistors that are connected in parallel. And from this, we get, this thing will write 1 amp. Any questions about this particular example?
No, sir.
All right, I'm going to go ahead and move on to that last example problem that I want to do for today then, because it includes the next thing that I wanted to show you guys as kind of a way to make sure you're doing current division right. So this is going to be a big, ugly looking circuit, but we'll be able to get through it actually pretty quickly. So let's say that we have the following circuit. Hundred kilo ohms there. 20 kilo ohms here. This voltage is 0.5 Vx. Let's say that this guy is 5 milliamps. This is 3 kilo ohms. This guy is 7 kilo ohms. And out here is a 2 kilo ohm resistor. And I'm going to define the X to be the voltage drop over just the 3 kilo ohm resistor. And our ultimate goal is to find this voltage, Vy. Okay, so let's start by saying that we can solve for Vy using voltage division, because that left-hand portion of the circuit, let me scroll up here a bit, looks pretty darn close to what we did here in this example, right? So we're going to follow that in effectively the exact same way, all right? So I'm going to say that my voltage Vy is going to be my known voltage, which in this case is 0.5 times Vx multiplied by the resistance I want, which is the 47 kilo ohm resistor, divided by the total series resistance seen by that dependent source, which is 47 kilo ohms in series with the parallel combination of the 100 kilo ohm resistor and the 20 kilo ohm resistor. And 100 plus 20 is 120 kilo ohms. give me just a second. Let's see, 47 divided by 47 plus 100 times 20 over 100 plus 20. All of this is multiplied by 0.5. Gives me, this is going to be a little bit wacky, but I'm going to have 141 divided by 382 times Vx, which is the same as 0.369. So my Vy is related to Vx by that factor, based entirely on the ratio of resistances, because I found it using a voltage division method. Now let's look at the right-hand side of the circuit, which is going to help us figure out what Vx is. Okay, so I would argue that Vx would be most easily found by determining the current that I've just labeled as Ix and then multiplying Ix by 3 kiloohms. Anybody see any problem with that basic Ohm's law methodology there? I'm going to assume your silence means that you're okay with what I'm doing. So I have a known amount of current, 5 milliamps, flowing into a network of resistances, right? And so I see 3 kiloohms in series with 7 kiloohms, or a total resistance of 10 kiloohms in parallel with 2 kiloohms. So I can find Ix using current division as well. So using current division, Ix is going to be my known current, 5 milliamps, multiplied by 1 over the resistance that I'm interested in, and this is where things get tricky per se. So I want the resistance of this branch because that current Ix flows through this middle branch. So that's going to be 3K plus 7K. And I divide this by 1 over all of the resistances in parallel. So that's 1 over 3 kiloohms plus 7 kiloohms plus 1 over 2 kiloohms. And if I do this, I get my answer to be 5/6 of a milliamp, or 0.844, I think. .8333, sorry. From this, Vx is 5/6 of a milliamp times 3 kiloohms which gives me 2.5 volts. And I can substitute that in up here, and I find finally that Vy is equal to 0.923 volts. So, any question regarding this example? Now, well, yeah, I'll stop talking here for a moment and let you guys say something if you choose to.
It looks messy, but I don't think it's impossible. So
Yeah, it
Let's
definitely,
move on to that.
yeah, it just takes practice for sure. And you guys are going to get a lot of practice.
Yeah.
That being said, yeah, so what I'm going to talk about tomorrow, I've decided to move some things around. What I'm going to talk about tomorrow is an analysis technique called nodal analysis. Nodal analysis is effectively a method by which to solve circuits with multiple unknown voltages by using multiple applications of Kirchhoff's current law. Then on Thursday, I'm going to cover what's called mesh analysis, which is where we solve a circuit for multiple unknown currents using multiple applications of Kirchhoff's voltage law. Nodal and mesh analysis right now will honestly probably make more sense to you than current division and voltage division. They are a very, very powerful tools in your circuit analysis toolkit. But for the third section of class, wherein we are analyzing steady state sinusoidal circuits, we are going to fall back on these principles of current division and voltage division very, very heavily. Because I can tell you that using mesh and nodal analysis, solving systems of equations that involve complex numbers is extraordinarily difficult to do by hand. Your calculator literally cannot do it. So to do it, you either have to come up with creative tricks to make the circuit seem easy, which is where voltage, current division, and stuff like that come in, or you have to use a computer. So we're going to put these analysis techniques on the back burner for a bit, to be entirely honest, and I'm probably going to have to revisit them again when we use them, but I will try to intersperse them, example problems that use these principles throughout my lectures so that we can kind of come back and revisit them, because your instinct as students is usually to use nodal analysis and more so mesh analysis to try to solve for any and everything because of how powerful that tool is and really how easy to implement it is. So I would encourage you to look at this stuff and try to wrap your head around it. But I guess what I'm saying is right now you don't have to spend a whole heck of a lot of time learning this because you're about to learn something that's really transformative in the way that we're going to look at and analyze circuits. But these tried and true methods, just based on really the simple application of KVL, KCL, and Ohm's law, can really get you a long way in an awful lot of circuits. So yeah, I would really endeavor working homework set number 4 from on the web work or whatever, actually using the source combination techniques and the voltage division and current division techniques and stuff like that before we learn nodal and mesh, because you're going to want to use them absolutely everywhere. And technically there's nothing wrong with it, but sometimes setting up a system of equations and solving it is overkill for something that we could easily do using current and voltage division. And I'll explain what I mean by that, probably more so tomorrow and Thursday. So with that being said, does anybody have any further questions on any of this material or any questions regarding a homework problem or anything?